From the examples we have discussed, it was very clear that to provide enough capacity to a governor mechanism so that it can manipulate the valve mechanism or the other control mechanism for the system, it is necessary to put substantial amount of weight. That makes the governor bulky, very heavy, and so on. On the other hand, I think the possibility exists that if we also take the help of springs to generate the at least a part of the control force, because the weight of a governor mechanism which is added to the sleeve, its primary function is to bring the governor to the lowermost position or to effectively develop a control force which takes the rotating sphere to the towards the axis of rotation. So, I think another class of centrifugal governors have been developed, where springs are the predominant factors or agents for creating the control force. Today we will discuss two important such governor mechanisms which fall in the class So, this class of governors also operate on the basis of the deflecting force, which is nothing but the centrifugal force, but which are controlled predominantly by springs. There are two types of governors which are commonly used. The basic sketch representing this I will draw only one half of the So, in this type of governor, you see that the rotating sphere is connected to a bell crank lever which is hinged at this point, which you may call O, which is connected to a cover which is rotating along with the shaft. So, the whole body, including this one, is rotating just like a rigid body. This ball is pressed again, a spring which rests one side is to the casing, other side to the ball, so that it applies a pushing force in this direction, and the sleeve which is going to be operated by this lever, that ultimately controls the valve mechanism. So, this is the type of spring controlled governor. Of course, there is also some mass m, and this is mass m. This is the spring of stiffness k. This length of this arm is b, length of this arm is a. And this type of governor is called Hartung governor. So, schematically, in a deflected position, that means when it is rotating at a particular speed, this length is B, this length is A. At any instant, this angle is, say, theta. Now, the force acting here from the spring will be, say, P, depending on the initial compression and the amount of total compression, and half of the sleeve weight will act here, which will be mg by 2. The other half will be taken care of by the other direction. We also mention here that when and at any instant, of course, we should also remember that r is nothing but the radius at which the sphere is rotating. So, now we have to find out what is the effective control force expression. That means the effect of this sleeve weight, effect of the spring together, or maybe gravity also, but we neglect gravity in this analysis, but it is also there. So, what will be the equivalent control force as a function of r? Let us find out that, because once you find out that, the equilibrium position will be given by the condition that the m omega square r is equal to Fr. So, we have seen that the stiffness of the spring is K, and spring force is equal to 0 when r is equal to c. That means its natural length is such, and the fitting or the location of this hinge, etc., are so that when r is equal to c, then the spring force is 0. Let us try to derive the expression for control force. As we have done before, we will do the same thing. That means to find it out, what we will do, that the moment produced by this equivalent force about this hinge point O will be same as the moment produced here by the actual forces. So, therefore, taking moment about O, what the actual forces are producing will be P into, now this length is B and this is theta again. So, this height will be B cosine theta plus this weight is mg by 2, this force, and the arm length will be A cosine theta, and that must be equal to the equivalent control force. If all these things are removed and an equivalent force is produced, its moment will be B cosine theta. So, from this we can write F is nothing but P plus now we also know that P is 0 when r is equal to C. So, when r is equal to r, what will be the P? That means the compression which the spring has undergone. That means originally, or the length of the original length of the spring let me represent it by this one. That means this is C. So the compression, when it comes here to R, compression of the spring is R minus C, and that multiplied by the stiffness has to be the spring force. So finally, the control force Fr is expressed as K into R minus C plus but we have to keep in mind that this is approximate. Why approximate? Because we have ignored the effect of this mg, assuming that this mass is not large. So if this is the expression of the control force, how does it look like if we plot it? Very clearly you can see that it is a straight line. If you plot F versus R, it is a straight line because this is a constant, this is a constant, simply Kr is the term which is varying with R, and therefore obviously this angle is nothing but insuitable units of course. And the intercept length is, that means where F is equal to 0, R is equal to at this value of R, Fr is equal to. So now we find the equilibrium condition. For equilibrium, we know that the only thing which we have to do, m omega square R has to be equal to Fr, or this is equal to K into R minus C plus and this gives us the equilibrium speed and R relationship. So therefore, we can find out what will be the equilibrium speed very easily, because this will be your m omega square R, and obviously this is the equilibrium speed, equilibrium radius R for a particular value of omega. As the speed increases, R increases, and it is quite obvious. Now you see, there is a possibility, because this quantity, that is the length of the original length of the spring, stiffness of the spring, the length of these bell crank levers A and B, these are all adjustable things which we can control at our will. So if that is done, so if C, A, B, K, etc. are so adjusted that C is equal to, including M, M, G, A to B, to B K. So if we do that, then what happens? Then this becomes 0. So control force diagram will now look like this. So what does it indicate? That the system can have equilibrium condition only if the deflecting force is also coincide with that, and that indicates, we have already seen, this kind of a situation is called isochronous situation, or the governor is isochronous at this speed. So we find that df dr is equal to f by r was the condition for isochronism, and df dr is nothing but k. df dr is nothing but k, and f by r is equal to, f is equal to fd at equilibrium, which is m omega square r. So m omega square r by r is m omega square. This is a isochronous operation, so we call it omega s. And so the isochronous operation of this is achieved, and the speed, isochronous speed, is given by this quantity. Now this obviously isochronous means it will be very sensitive and so on, and by suitably adjusting various, we have lots of parameters at our disposal, and therefore m need not be a very large value, as you can see. So we can make the whole thing compact and also sensitive and useful. Another type of spring control governor we will consider, which is also used in many cases, the configuration of that I will draw the schematic diagram to save time. This is the spring. Here the sleeve is actually pressed against a spring which is prevented from going up by this cap, and which is actually covering the central axis of the governor mechanism, and the sleeve moves up and down, but this sleeve is subjected to a spring force in the downward direction instead of the gravitational pull of the large mass which normally we keep here. So, we have replaced that by this. The rest is very similar to the other kind of governors, that is a bell crank lever. At the free end there is one spherical mass of m. At any instant the radius at which the sphere is rotating is r, the lengths are this, and at a tilted position at any particular RPM when it is rotating, it is inclined like this. So, now again our usual procedure we will follow, that means we will now try to find out an expression for the control force. So, therefore, control force, if we consider that whatever moments are being produced by the actual forces, which will be same as the produced by the moment by the effective control force. So, we will take K is equal to spring stiffness as before. Now, F into, if we take moment about this point O, which is nothing but B cosine theta, that must be equal to the actually moment produced by the actual forces. So, this will be P by 2, why P by 2? Because half the force of the spring is being taken by this bell crank, other half by the other. So, it will be P by 2 into A cosine theta minus, now this moment is in the opposite direction, it is mg B, and this distance will be B sine theta. So, quite straightforward, we get the expression for the control force as now again we know that spring force at any particular position will be given by, now P0 is the force when angle theta is 0, corresponding to that position. At that time the spring force was P0. So, when angle is now theta, this is the further compression of the spring is A sine theta, and that multiplied by the stiffness is the further spring force. This total spring force is this, where P0 is the spring force So, therefore, the expression of the control force now we have also used the condition, this sine theta, A sine theta, this one. So, how we have done it? We have, because we know as sine theta has been replaced by, how much is sine theta? Sine theta is same as sine theta. Now, if this length is P, this is R, so this length is P minus R, and this is B. So, P minus R by B is sine theta, or R minus P. So using this, in this expression, this and this, we finally get the expression for control force. Now it is, if we want to plot, we will have certain problems. It is, so far as up to this is concerned, it is fine. But theta and r relationship is not that straightforward. So what we can do, let us do a first approximation in which we ignore this effect of this mass, then how the control force looks like. So the first approximation we will do, or mg is neglected, the mass is not substantial, then obviously the control force becomes a simple linear function. And this slope is given by tan inverse k a square by 2 b square. And we can also find out this. This will be simply when r, this f is equal to 0, when f is equal to 0, how much will be r? R will be simply E0 a by 2b minus p, or sorry, plus p will be E minus, I am sorry, E0 b by k a, something like this, I think. So I think this is, if we can consider this effect of the weight to be negligible, we will get this. Next, if we want to improve our situation, suppose we want to make not that drastic an assumption. Second approximation, what we will do, we will treat tan theta is approximately equal to sin theta. Which is possible in case of theta's value being small. If we make this approximation, then you will find expression of Fr will be now this tan theta can be replaced by sin theta, which is again nothing but r minus p by b. Now you can take the terms containing r common, and finally the expression for control force will be this. Now, if we plot this second approximation, we see that it is still another straight line because it is linearly dependent on r. Only thing now, the slope of that straight line, that means df dr, is going to be k square by 2b square minus mg by b. That means here the slope was k square by 2b square. Now it will be somewhat less. So therefore, we will get another straight line whose slope is slightly less than this. So therefore, at this point, we may call it A, these two curves, the result of the values for the two curves, they match. If we do the exact analysis, then you can show that the true curve will be something like this. So, the result of an exact analysis, if you plot f, you will find this will be the curve where it will pass through the same point and its slope will match with the slope of the second approximation, because when theta is very small, then this approximation becomes exact, and so the slopes will match. So I think if we examine this a bit more carefully, the exact curve is something like this. Then if we draw a tangent to this FR curve, what does this indicate? This indicates a particular speed. That means this is nothing but the deflection or deflecting force, which is the centrifugal force. So it is obvious that this is the speed at the operation has to be, to have any equilibrium operation, the speed has to be below than this, because otherwise Fr can never be equal to the centrifugal force, as you can see that. And it is also very clear from this that this is the critical R or radius of operation beyond which the operation is unstable. Now I hope you remember that if we take a speed something like this, then the equilibrium is given by this. Now here it is obvious from this nature that df dr is less than, in this region, df dr is less than f by r. Because df dr is this slope and f by r is this slope. So therefore, it is unstable. Whereas if we operate here, you can see that df dr is more than the f by r, which is nothing but the slope of this. This is f, this is r. So this is the table. And limit of stable operation is this. Now, one more thing we should find out from this is that this location of this point A means what? That the two curves with first approximation and second approximation, they give the same value. Now, it is very clear that they will give the same value of the force when, and that value will be equal to, that means for A at A F R first approximation is same as F R the second approximation. This will be possible only when R is equal to P. We will see that only in such case the two approximations will give same value of the force, which is nothing but value of this will be this. So therefore, location of A is indicated by a value of R, which is P is given here, is the distance of the hinge from the axis of rotation, small p. Now, if it so happens that P is such, that means location of A is such, that if you join or if you pass a tangent through that, it will also pass through point O. This implies that at this location it will have isochronous operation. Because here df dr is this and f by r is also same. So therefore, it satisfies that condition, and the governor is very sensitive, and obviously sensitive means that it will operate better. Now, another important point that we are improving, we are trying to increase the sensitivity. But there is a limit to that, and we have to be very careful about increasing the sensitivity as much as possible. And that particular situation, that means where sensitivity is high, we may, or the governors are susceptible to a particular phenomenon which we call hunting, and let us see what is that. Now, we have seen that how a governor functions when a system is running. Suddenly, due to some reason, maybe a change in the load or change in the input, whatever it may be, suddenly maybe the load is less. So, governor will try to speed up, and as it will try to speed up, we are controlling, cutting down its input. So, therefore, then it will again start coming down to the required level of speed. But due to the finite inertia of the whole system or mechanism, it does not stop when it reaches the required speed. That means graphically we can explain that if we plot with time the speed. So this is our required speed, and we are somehow here. So what we do, we are trying to cutting down the input so that speed reduces. When it comes here to our desired operational speed, it does not stop here because the whole system will have some inertia. So it continues, it goes below the desired speed, but again, since it has become now less than desired speed, input will be increased, and then again slowly it will change its range and it will try to come here. Again, due to inertia, it will overshoot, and this will cause the whole system to hunt. It will not asymptotically stop. The ideal situation would have been we start here and then we reach this, but that will not happen, and the phenomena of hunting becomes more prominent in certain cases, particularly where the natural frequency of the system matches with the frequency with which the power or the requirement load, etc., are fluctuating. That is a serious thing. So in normal case, it will be like this, and it will gradually come down and get damped as it happens with vibration. So it is supposed to become like this. But if the fluctuation in the load, etc., is also continuing, then this will also continue. So this will continue following the load fluctuation. And when the two frequencies, that means the frequency with which the load is fluctuating and the natural frequency of the system, they match, then the problem can be quite severe. Now, how to find out the natural frequency of the governor, its operation? We can do an approximate analysis like this. So this is the spherical ball, and the forces are, as we have seen, that in the equilibrium position, this is F and this is m omega square r, this is r. Now, say due to some disturbance, it has shifted here. So this force will be now what? It will change, it will be force at r plus the rate at which force changes with r, and the amount of change in r is x. And this is m omega square, which is same because speed has not changed, only the displacement has been provided, will be r plus x. Now, if at operational speed omega, by definition F is equal to m omega square r. That was an equilibrium. What we have done, we have given a displacement, and we want to see how it changes, what frequency, that will be the natural frequency of the system. That means if a governor operating at a speed omega at a particular r, if we displace the mass, spherical mass, and then we will find that this spherical mass will oscillate about the original equilibrium position, that will give us the natural frequency. Now, one thing we have to keep in mind, the mass of the whole system represented by this is not the mass of the sphere, because there is certain amount of matter present in the linkage, certain amount of matter present in the sleeve, all those things. So all the equivalent amount of inertia is accumulated on this body, and therefore we consider that its mass is equal to MEQ or equivalent. But the centrifugal force which is produced, which is trying to displace the whole thing, is actually the mass of the spherical ball only, which we call M. So now, what is the total force in this direction? It is m omega square r plus x minus f minus df dr into x, and this total force in this direction must be equal to the mass of the whole inertia of the system represented here into its acceleration. Now, displacement from the equilibrium position is denoted by x, so the acceleration will be denoted by x2 dot. Now, here we get, or m equivalent x2 dot is equal to m omega square r minus f is 0. So, what remains is m omega square x minus df dr into x. Rewriting, so rearranging this, we get and we know the solution of this equation is when, of course, df dr minus m omega square is a positive quantity, then it is a harmonic function of time we get with the natural frequency of oscillation is given by 1 by 2 pi So, this is a standard equation mx2 dot plus kx equal to 0. So, the natural frequency is square root of k by m, which happens to be this, and natural frequency in hertz will be 1 divided by 2 pi multiplied. So, once this frequency becomes very close to the frequency with which the load fluctuates, then the whole system will undergo a resonance. That means, the whole governor and the whole engine system will hunt or fluctuate in its speed and operation. I think this brings us to the end of our centrifugal governors, but you remember that we mentioned that it is possible to achieve much higher sensitivity or response if we base our operation not on the change in velocity, but rate of change of velocity, that is acceleration. So, rather than waiting that velocity will change from one value to the other and taking that change and making our system to be based on that, a better situation we may get if the rate of change of velocity which we can sense at any instant, if we can sense that and operate our governor or governing mechanism on that. So, I will just give one quick example of an inertia governor. This type of governors are called inertia governors or flywheel type of governors. I will not go into the detailed analysis. I will only indicate the basic features of such systems. So, this is like a disc mounted on the shaft and it is rotating in this direction at speed omega. Now, there is a lever hinged at this location, say let us call it A, and there are two masses mx and my at these two ends, and this is again controlled by a spring which is attached to this location here. Now, what happens if it tries to accelerate? That means, suppose the load has increased or decreased and this system is trying to accelerate. That means, there is an acceleration alpha. So, if it tries to accelerate in angular direction, what we can do? We can again analyze the system by bringing it back to an inertial frame using D'Alembert's principle. So, everything in this will be acted upon by an inertia torque in the opposite direction. It is a very standard technique of solving problems in an accelerated frame of reference. I will not draw the whole thing, but what it is going to be now, if the whole system here, everything is subjected to an opposite inertia torque, then this well crank lever or this lever will obviously rotate about this hinge point. So, it has rotated by an angle theta, and this change in configuration can be sensed, can be picked up to operate the valve or input mechanism. So, here you will find that this we will not go into the derivation, but you can definitely try find out that what will be the relationship between theta, which will be a function of alpha. So, moment it tries to accelerate, as soon as the load changes, immediately it will come back to a position. It does not have to wait till the speed changes to some suitable value and then sense it. So, it is definitely much quicker in response. So, this type of governors are called inertia governors or sometimes flywheel governors. So, I think this will be an interesting exercise. You assign various dimensions and then find out an expression of this angle of rotation in terms of a function alpha or in terms of alpha. There are other mechanisms by which you can have speed control in small devices. As I mentioned, in such cases there is not much scope of controlling the input, because input may be a spring which you have wounded and that spring load is gradually reducing and you want to maintain the RPM same. So, they are used as energy dissipative systems, we call. So, just the basic principle I will explain, and there are various models using the same principle. So this is rotating the shaft coming from the system, and there are two leaf springs, very thin spring, leaf spring. At the end there are two brake shoes kind of thing. The length of this can be adjusted so that sometimes it can go nearer to this cup and sometimes it can be away. Now if the speed of this increases because load say or it decreases, whatever it may be, then what will happen, the centrifugal force acting on this will try to, if it increases, try to fly it off. So moment it happens so, what will happen, it will press against this fixed cup and more energy will be dissipated. So therefore this larger torque coming here will again lower down the speed. Similarly on the other hand, if the speed tries to decrease, then obviously as it decreases, then this will come nearer and the pressure here will be less and less torque will be developed here, so speed will increase. So in this way what will happen, that system will not be allowed to go beyond some design speed which is decided by adjusting the position of this. If you take it too much, and obviously you will find it will press harder. If you take it to this side, obviously this will come below and it will press at a lower pressure or with lower force. So these kinds of systems can be very small and miniaturized, and in many small toys the similar system or in a modified form also sometimes it is found, but the basic principle is same, that moment speed tries to increase, more energy is dissipated, more friction torque is developed. So this is another way of controlling speed and which is used in many devices. So that brings us to the end of our discussion on how to control the speed of a system when there is major change in either the output load or there is a change in the input condition. So therefore, if we provide a proper governor, the system or the engine will run at a right kind of speed for which the system was designed, implying that the efficiency with which it will work will be highest.